Welcome back everyone to another video in our FE Civil Preparation course. In this video, we are going to talk about normal strain. Strain is a quantity that describes the deformation in a body in response to an external force. Strain is the relation between the change in dimension and the original dimension. Hence, it is unitless because it is a percentage of a change. If we have this beam in this picture, and we apply the normal tensile force as shown, the beam will extend with an amount of delta L. It is important not to confuse between delta L and the strain, as delta L is the change in dimension and it has a unit of length, while strain is the rate of change and it shall equal to delta L, which is referred to by the Latin symbol of delta, over L, which is the original length. Hence, it is unitless. Stress and strain are closely linked with each other. The relation between the normal stress and the normal strain is known as E, which is the Young's modulus of elasticity, and it represents the amount of stress required to be applied on a material to develop a certain normal strain. Young's modulus is a unique mechanical property of each material. Based on above, and as E, which is modulus of elasticity, equals to stress over strain, and we know that normal stress equals P over A, while strain equals delta over L. Hence, E equals to P over A, all over delta over L. Solving this equation, we can conclude that delta, which is the linear change in length of a member under normal stress, equals to P multiplied by L over E multiplied by A. And this is called Hooke's law. Any normal deformations in a body will result to other deformations in the lateral direction. In this video here, you can see if we apply the compression force on a body and the body started to shorten in the longitudinal direction, the body will start to expand in the perpendicular direction. We call the main direction the axial direction, while the perpendicular direction is called the transverse direction. The same will happen if we apply tensile force on the member and it starts to stretch. The body will start to shorten in the lateral direction. The relation between the axial and the transverse strain was found to be constant for each material, and it was called Poisson ratio, on the name of the French mathematician Simon Poisson, who formed the ratio between the axial and the transverse strain. Poisson ratio is a mechanical property for each material, and it ranges from 0 up to 0.5, and it was given the Greek symbol of mu. And now, let's have a couple of examples of this.
So let's check this example. We have 2 meter long aluminum bar with modulus of elasticity of 69 gigapascal, and it is subjected to tensile stress of 175 megapascal, and we want to calculate the elongation. It is very important to note if we want to calculate the strain or the elongation, because you know these are two different parameters. We will start by the known information. As always, we know that E here equals 69 gigapascal, and we know that the length of the bar is 2 meters. We know that sigma equals 175 megapascal. We know the equation for Young's modulus. It is Young's modulus equals stress over strain. So the 69 gigapascal, we have here the stress per megapascal. So let's transfer the 69 gigapascal to megapascal. So we'll multiply by 1000. It is very important to notice the units in this chapter. This will equal to the 175 megapascal over the strain. So we can calculate that the strain will equal to 2.5 multiplied by 10 power minus 3. So now we have the strain and we have the length of the bar, and we know that the strain equals the elongation or the delta over L, which means that delta equals the strain multiplied by the length. So this will equal to 2.5 multiplied by 10 power minus 3 multiplied by 2. This is 2 meter. Let's multiply it again by 1000 to transfer it to millimeter, because we know that the answers here are per millimeter, and it is logic that the elongation, it will be a very small value. So solving this equation will come up with the value of 5 millimeter. So the answer is number B, 5 millimeter. Let's check another example. We have here this steel rod with E equals 29 multiplied by 10 power 6 psi, and it is subjected to load of 30,000 pounds. We want to calculate the minimum rod diameter needed, so the rod elongation cannot be more than 0.2 inches. So here we have a specific strain or specific elongation we don't want to exceed, and we want to calculate the area of the rod. So let's start by the data that we know. We know that delta equals 0.2 inch, because this is the maximum allowed delta. And we know that the length equals 10 feet. We know also that E equals 29 multiplied by 10 power 6 psi. And we have P equals 30,000 pounds. So we will start by directly applying in the equation of delta, which is delta equals P multiplied by L over E multiplied by A, which is Hooke's law. So this is just a direct equation. Based on that, we can calculate that the area equals PL over E delta. So the area it will equal to the 30,000 pound multiplied by 10, which is the length, but we have the delta per inch, so we can transfer this length, which is feet, to inch, so multiply again by 12. This is over the E, which is 29 multiplied by 10 power 6 multiplied by 0.2, which is the sigma. It's very important again to make sure that all units are consistent. Here the youngest modulus, it's 29 multiplied by 10 power 6 psi. Psi is pound per inch square, and we have here the force per pound, and we transferred the length, we make it inch also, and we have the elongation per inch. So based on that, we will get the area in inch square. So this is 0.62 inch square. This is area of a circle, so it equals to pi d square over 4. Solving this equation, we get that D equals 0.89 inch. So this is it for our video today. Thank you.